Welcome. This video explores a couple issues of numeric weirdness that you should get used to. So, the second half of that mental code worksheet has this debugger practice that focuses on just evaluating simple expressions. Now, 3 plus 1, I would predict that's 4, and indeed it is 4. That shouldn't come as a big surprise. And some of these are pretty straightforward. If you know what this operator means, that means the modulus or remainder operator, this is pretty straightforward. Divide 3 into 10. It goes in 3 times with a remainder of 1. So the answer here is the remainder. The answer is 1. All right, so some of these are straightforward as long as you know that this means division, this means remainder, etc. Other of these are a little bit trickier. And so this worksheet is designed to allow you to possibly get tricked a couple times, but get used to some of the oddities of doing math in a programming language like C++. So, I'm going to introduce you to a couple of the ideas. The first one is related to this wonderful comic from XKCD. Google it, XKCD. If you've never heard of it, wonderful way to kill an afternoon is reading old comics. So this character's counting sheep. Going up, 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 hits 32,000, and the next sheep is negative 32,000. The joke here is that this is how computers think about numbers. We have different formats of number. Most commonly, we're going to use int and double, but there are all kinds of other versions. So if we want to represent a whole number, we use an int. If we want to represent a decimal number, we use a double. And if we want to represent a whole number, but we don't need the full storage space of an int, which is 32 bits on most PCs, then we could use a short, which only uses 16 bits of storage. Now, kind of how much storage space we have controls how big a number we can represent. So integers go up to 2 to the 31st power minus 1. They go up to like 2 billion, and then after we go past this value, they wrap back around to negative. If we're dealing with a short, we go from 32,767. We can't represent anything bigger, so if I add 1 to this value, I wrap around and become negative. So one of the things you have to watch out for if you're working with large numbers is overflowing your storage and wrapping around from positive to negative or from negative back around to positive. The next bit of weirdness is division means two different things. If we divide a whole number by a whole number, that is to say an int by an int, we get a whole number answer. Basically, we ignore any fractional part. How many times can you divide 1 by 3? 0 times. All right, and well, normally we think of a decimal portion, but if we're dividing two whole numbers, we only get the whole number part. If we divide two decimals, two doubles, by one by another, then we get a decimal answer, a double. If one of the two, at least, is a double, we're going to get a decimal answer. But it can be really easy to do something like divide 1 by 3 and assume you're going to get 0.333, but actually get 0 because you're working with two whole numbers. Next oddity is floating point numbers. When we're working with a double, right, one of these decimal numbers, these are also called floating point numbers in programming. These are always approximations. And they're usually pretty good approximations, but they just about always have some amount of error. And that's because fundamentally the way they're represented is something kind of like this. We have the twos, the bits that normally represent the powers of 2 for the parts greater than 1 or greater. And then we also have the part to the right of a decimal point, like 0.1010, that represent fractional parts. So we've got halves and quarters and eighths and sixteenths, and that's how we build up a decimals, by adding together these inverse powers of 2 to try and get what we want. Now, if I only have 4 bits of storage to the right of my decimal, then I can only represent, I go from showing something like 0.625 to the next smallest value I could represent would be to take this away and put a 1 there, so 0, 1, which would look like this, which would mean 0.5 plus 0.0625, which would be 0.5625. There's no way for me to represent 0.6. I go directly from here to here. Now, in real life, we have a lot more bits to use than that, so we get more accurate, but you will find that there's times when things that seem pretty simple and straightforward, instead of adding two values and getting something like 3.0, you may get 3.000000001, and this would be why. The last big thing to warn you about, easy mistake to make, especially if you're used to using like a TI calculator, this symbol does not mean exponent in C++. It's actually bitwise exclusive OR, which you don't have to worry about, but if you're curious about what it's doing, that's what it's doing. And so if you try and write an expression using this for exponent, you will get weird results. So how do we figure out what is right? Same story. If I want to test something, I think I know what this expression should be, but I want to see. I just need to put it in Qt Creator and run it with a breakpoint so that I can see what we get by doing 1 plus 3 times 2. So I will start it up with rebuild this, start it up with a debugger, and it hasn't run this line yet, so X has got just a random value because we haven't actually set it yet. So I'll step it to run that line, and we got 7. All right, just like normal math, we have to multiply first. 3 times 2 is 6, plus 1 is 7. That's why we got 7. So you definitely should read each of these, try and predict what value you expect it to come up with, and then test in the debugger and see kind of the important thing to see here is when you're wrong, when your intuition of how math should work is different than how the computer actually does it.